In this video, I'm going to show you how to calculate the adjusted confidence intervals from a one-way within subjects ANOVA so that you can present them in a graph. Now, I've already covered how to calculate the adjusted standard deviation, which is important information to execute this procedure. And in the previous video, I calculated that to be 12.738 for the Weatherall et al. Study. Now that I've got the standard deviation, I've got to follow two computational steps, which are convert the original scores into z-scores, and then transform the z-scores to have the values of the means from the raw data, and then the adjusted standard deviations. So that step is a little bit more complicated than the first one. So let's just do the first one first. Go into Analyze, Descriptive Statistics, Descriptives, and put the three variables into the Descriptives box, and make sure you click down here, Save Standardized Values as Variables. Now I'm going to have three variables that have been converted into z-scores. So pretreatment is now z-pretreatment, and it's in z-score format. So the next step I need is the second step, which is to transform the z-scores to have the mean values from the raw data over here, the pre-adjusted scores, and the adjusted standard deviations, which I've calculated to be 12.738. So first I need to get the means from the raw data. So let's just get the means for each one. We don't need anything else. So here are the means, 44.94, and that's pretreatment. And the pretreatment standard deviation is now going to be 12.738. Post-treatment, the mean is 25.33, and that standard deviation needs to be 12.738. And finally, follow-up has a mean of 24.83, and it needs a standard deviation of 12.738. So I need to convert all the means into the raw score means. I can't change the means. That would be changing the analysis in a fundamental way that's not consistent with the within subjects ANOVA. So now that I've got the means, I need to transform each variable individually through the compute variable. So I'm going to call this pre-treatment adjusted. And I'm going to start things off with that variable's mean, which is 44.94. 44.94 plus the product of the z-scores for that pretreatment variable and the standard deviation of 12.738, which is going to be the standard deviation for every variable. So 44.94 is going to ensure the mean stays the same. Recall that a z-score has a mean of 0. So by adding 44.94 to all the scores, they're going to have the mean of the raw data, and the standard deviation is going to be transformed. So let's click OK, and we have a new variable here called pretreatment adjusted, and now let's check the descriptors for that variable just to make sure, show you that it worked. So now that variable, let's check the mean and standard deviation for that variable. And we can see that the mean is 44.94, which is the raw score mean. Nothing's changed with the mean. You don't want to change the mean. But the standard deviation is 12.738. It was originally 20.38. In the raw scores, 20.38. Now it's down to 12.738. And that's the power of the within subjects design, is that it reduces the size of the standard deviation, which reduces the standard error of the mean, which reduces the mean square error in the ANOVA. Therefore, you get a bigger chance of rejecting the null hypothesis. That, of course, is true only if the correlations between the conditions is positive. All correlations need to be positive. Not all of them, but on average, it needs to be positive. So we've transformed the first variable. Now we just need to transform the other two variables. So now we need post-treatment adjustment. So that mean is 25.33. 25.33. I need to get rid of this one and replace it with the post-treatment z-score, and that's going to be multiplied by the adjusted standard deviation. And now I'm going to do it one more time for the follow-up data. Follow-up, that mean is 2483. 24.83. I'm going to keep that adjusted standard deviation and just replace the follow-up. And click OK. And now let me double check that my adjusted variables are in fact what they should be in terms of means and standard deviations. And we can see that the means are all the same. So pre-treatment 44.94, 44.94, post-treatment 25.33, 25.33, follow-up 24.83, follow-up 24.83, and the standard deviations are now all 12.738. So now that I've got those adjusted standard deviations, SPSS, or any other program for that matter, can calculate the adjusted confidence intervals for this analysis, which I'm following it up as a one-way within subjects ANOVA. I should point out that SPSS will calculate line chart for you, so time 3, but it doesn't have confidence intervals. So if I use the raw data and I click on plots, add that, it will give you a line chart, but it doesn't have the confidence intervals, and I'm not familiar with an obviously easy way to add the confidence intervals to this particular chart. But you can go into Graphs, Legacy Dialogues, Line Chart, and click on Summaries of Separate Variables. Keep it simple, Summaries of Separate Variables, click Define. And I'm just doing the raw data right now. I'm going to do the adjusted second. Put lines represent these 3 means, and click on Options, and then Display Error Bars, and we have confidence intervals here. And that's probably all you'd ever report. Like some people report standard error. I have no idea why they do that. Confidence intervals is really the most informative thing to do. And I'm going to click Continue and OK. Now again, these are not on the adjusted data. Let me just clean this up a little bit. And change the scale to 100. Now this doesn't look exactly like what I reported in the textbook, but it is similar. You can see that the means are dropping, but the confidence intervals are quite large. And this is, you would never think really that there's, there might not even be a statistically significant difference between these 2 means based on looking at the confidence intervals. Even though the one-way ANOVA is saying that there is, I don't know, it'd be close. Maybe it is. But it's not reflective of the ANOVA, which is saying, look, there's definitely a statistically significant effect here. It's a huge effect size even. I didn't show what the effect size was in this video, but yeah, partial eta squared was 0.462. So looking at that plot, you'd never think that was true. You'd think, look, you just barely rejected the null hypothesis. So now we're going to do it with the adjusted data so that it actually reflects more closely to what we actually did, which is a one-way within subjects ANOVA, which takes into account the correlations between the levels. And I want to make sure that I've got my error bars, 95%, click OK. And look how much difference there is in that. And this is much more consistent with the within subjects ANOVA we just did. Change that scale from, is it 10 to 100? There we go. So look at the difference in the confidence intervals, 0 to 100, same chart. And you can see that the confidence intervals are much narrower. The lower bound and the upper bound aren't intersecting with each other. You can have some intersection and still have a significant effect, but here it's just very clear. So this error bar chart is much more consistent with this ANOVA. And so I recommend you calculate your error bars. I know it's a lot of extra work. It's not too complicated, but it's definitely worth it in my opinion.